Hello again, everybody. So I'd say I have like a medium amount of glassware. You know, I'm not here to brag or anything like that, but it's not, you know, it's not heaps and heaps of glassware, but it is quite a bit, and most of it is currently dirty, like it quite often is, because when you have a lot of glassware, you just tend to chew through it all, get to washing up and realize, oh shit. Anyway, over a year ago, when I got that random illegal shipment of glassware accidentally sent to me, a chem player challenged me to use all of those different bits of glassware across the year. And I thought, well, that'll be easy. So naturally I failed it, and I didn't use all those bits of glassware. And there's one bit of glassware especially which I've never used because it's what many people would term as useless, really. Even though they're pricey and look very fancy, they're kind of pretty useless. And that's the Graham condenser. So today, we've got an experiment that I'm doing because I'm interested in it, because it doesn't actually have to have any good results, unlike a lot of the other stuff I've been doing, which has been failing. So we're doing something just to boost my morale a little, but we're also trying to do something that uses the Graham condenser. I wanted to say all that to preface the setup before I show you, because honestly, it's quite ridiculous, this setup, but we're doing it because it's fun, all right? That's as much justification as I'm going to do, all right? So, yes. So we're using both my VigRow columns here, and they're both 30 centimeters. So we have quite a bit of column length. Then we have here the 40 centimeter Liebig condenser, which is actually broken. I was doing a sulfuric acid distillation the other day because the head temperature gets to like 300 or so, and then I'm air cooling this. The temperature gradient just caused it to break. So, but it's only the outer bit, right? So I can't pump any water through it. So I could repair as well, because all it needs to do is hold the water pressure in there. You can see there's a bit of hole in the glass there, but haven't got around to repairing it yet. It was not a good feeling watching that sulfuric acid boil and hearing the characteristic chink of breaking glass while I'm standing next to it. Not a good feeling, very sinking feeling. You think, ah, shit, everything's going to explode. But no, it was just the outer cooling thing, which is annoying, but in the grand scheme of things, it's fine. Especially means I didn't die of sulfuric acid. Anyway, so we come down here, and then it rounds this corner and goes down through our Graham condenser, which is going to be have the actual water pumped through it. Now, the reason I think Graham condensers are useless, and I think this is an opinion shared by a lot of people, is that they have to be used vertically. You can't use them horizontally, like with the Liebig here, because of the coils, and you can't use them on any sort of weird angles, and you can't use them for reflux. What happens if you try and use this as a reflux is, if you get a little bit of liquid condensed, it tries to roll back down, but because these tubes are very narrow, it actually continually gets pushed up by the vapors, so you don't get a very efficient reflux. That's why the all-in condenser, the good reflux condenser, is really wide so that the vapors and the liquids can pass each other, whereas in this case it doesn't really work at all well for reflux. And when you're using it on its side, you can see how all the liquid would just get caught in every single bump on these coils. Most of the videos on YouTube with this actually in it is people just using it incorrectly, which, you know, people point out in the comments and that sort of thing, but it just goes to show it how unuseful it is, really. The most common use is the incorrect use. Now, this bit of glassware is a little useless, but it's to do with the Graham condenser. So it sits on top of here and allows us to connect the head to the Graham condenser. The problem is, and I don't know why I know why it's designed this way, but it's just annoying, in that this has a really weird angle to it. It's hard to see when you just look at it, but it's like less than 90 degrees, so that if we have a setup like this where we have the head you know, on the angle like all sort of distillation heads are, and then, you know, this thing coming down at an angle, and then we connect this up to here, look at that angle. That means that our Graham condenser has to be like nearly 45 degrees, which is, you know, not what we want at all. If we have our standard vacuum takeoff adapter, we can see the angles are much less, and allows us to have the Graham condenser basically vertical there. So even though this is the first opportunity for this bit of glassware after over a year to actually be used for its actual purpose, it's not fit for its actual purpose. Really, what you need to use for a Graham condenser is you need another piece of glassware that's not the head and not the condenser, but like a head, a specialized head where this takeoff adapter is like straight, is just horizontal, so that this whole section is horizontal, and then you can have this thing on like a, you know, a sort of a 90-degree angle odd, and then go straight down. You know, who's going to buy that? I mean, to use a Graham condenser, you need two other specialized bits of glass for the Graham condenser. All right, enough talk about all this condenser stuff. What are we actually going to do? Well, with all this fractionating power, what we're going to try and do is distill petrol or gasoline. I'm going to call it petrol because I live in Australia. Petrol and gasoline are the same thing if you're ever confused. Now I thought, because I just got the petrol out of the jerry can we have around the place for like the mowers and stuff, and I thought it was 91, but by the color of it I can tell it's 95, because in Australia we dye all our fuels different colors depending on what grade they are. So the 91 is red and the 95 is yellow. In Australia we're idiots, but we're really smart in working out ways to cope with the fact that we're idiots, like dyeing everything a different color so we don't get very confused very easily. So what I'm going to do is I'm just going to put some medium temperature water in there. The room temperature currently is 36 degrees according to this. I think it's been out in the sun for a little bit, so it's not very cool. The fuel's been sitting around at 40 degrees for the last couple months, so we're really only caring about the things from 40 to 50, and I think that's where the majority of the stuff is anyway, probably like the 50 to 70 range. Also, I'm going to chuck a whole heap of ice in this bucket here, and perhaps put this vial in an ice bath as well, because this lighter temperature stuff coming over isn't going to survive very long out in an open vial at 30 degrees. Now I can see a whole lot of vapors coming out of there, so my cooling obviously isn't efficient enough. You can see that on camera. Yeah, sort of. Yeah, shit. Alright, well, I'm obviously not condensing anything. It's obviously flying through this column. What happens is there's a whole lot of butane in there that gets dissolved, and when you heat it up, that butane comes off. So, and butane is a boiling point of -10 or whatever, and we're not going through a dry ice condenser again. That's not at the moment. I'm over that. So we're letting it go. Oh shit, I forgot the ice. Fuck. Alright, yep, we'll do that. Fuck. Managed to get a really small amount of low boiling stuff before the whole vial fell over into the ice bath. You can see the very small layer on the top there. But yeah, not a whole lot is actually condensing and getting actually into the vial. We haven't actually gone up in temperature at all yet. And there's really not that much in the column. So we're still just getting up the really low boiling point stuff. It would be nice to condense a bit more of it, but Alright, the light's failing on me, and I've probably got half an hour more of light. It's not really coming over, it's just staying in the column, and I'm not really getting any product over, which is, because I'm using two Vigrau columns, so, this is a product of my own stupidity, really, and enthusiasm to try and use every bit of glassware in my lab. But I think maybe it would help if it was boiling a little bit better, so I'm going to do my old trick. I'm going to got some sand here. I'm just going to chuck some sand in the boiling flask to help it boil a little bit better, and hopefully we get more of stuff turning into vapors, and it comes up through the columns a little bit faster. As far as collection, we've managed to collect sweet fuck all. So you know how I said this video wasn't going to have to prove anything? Well, I still think we've lost. So tomorrow, I've got to pack this up because it's dark. Tomorrow we'll come back and we'll do the distillation on my heating mantle, which we can get this up to a lot higher temperatures than 90 degrees. And we'll see what else comes over. And I'll have to think very hard whether I use the Graham condenser tomorrow. I suppose I have to, because that's the point of this video. Okay, we're back out here on another beautiful day. Well, I mean, it's a bit hot, but it'd be a bit rich for me to complain about that. And we've got the heating mantle going this time. We've got the sand in there, so that's why it's not an issue. Didn't bother taking the stir bar out, but that's just me being lazy. And hopefully this time we actually get some stuff distilling over. But like last time, the real test is whether the Graham can stand up to the distillation task that we are asking of it. So we were distilling at about 56 degrees, that's this fraction here, then all of a sudden we see the temperature has dropped to about 44, and that's without the heating really being slowed down in there. So it does seem like there's fractions. It could just be a, you know, an artifact of the setup and the heating setup, but it does seem like there's fractions, because now when it gets going again, the next fraction will be above 56. It'll probably get to about 60 and start distilling over again. So I honestly thought this would be perfectly continuous. You know, the temperature just would rise steadily and we would just get a continuous drop of some random liquid. But it does seem to kind of divide up into at least 5-degree chunks. I think it's worthwhile talking about what's actually in petrol now we're distilling it. So in fuel, about 50% of the fuel is alkanes. So that's fully saturated carbons with all hydrogens and no double bonds. And about 30% of those alkanes are completely straight. This is probably the most common one, hexane. Or heptane is common in fuel as well. And then 70% of the alkanes are gay, like this one here is probably the most common of the branched alkanes. 2,3-dimethyl-pentane is apparently one of the most common branched alkanes. A third of the fuel is then aromatics, most common of which is toluene. Benzene is a very small component of that, but there's a large number of molecules that can be in there. Trimethylbenzene, you know, tetramethylbenzene. There's not really too many polyaromatics. You're not going to have any like naphthalene sort of derivatives because they start being solids and too high a boiling point. Then 1/12 of it, or about 8%, are cycloalkanes, most common of which is cyclohexane. And then the final 12th out of this, should add to 1 if I've done the maths correctly, are alkenes. So these have a double bond somewhere in the structure, and it's hard to say which are the common ones because, you know, there's just a whole mix of different ones. But this is, for example, one that could be in there. There's 1, 2, 3, 4, 5, hexene or whatever. And there's really nothing much else in there. There's not really any alcohols or anything water soluble. And there's no water in the fuel, which is good. There are some additives, but they're, you know, way down in concentration. There's some weird rules about ethanol, depending on the countries. In Australia, we really have a very low ethanol content in our fuel, and that's because it's in law. You can't really put too much ethanol in the fuel. Actually, I don't think you can put any ethanol in the fuel. You can put a maximum of 10%, but then you have to sell the fuel as 10% ethanol fuel, and people are very... Here, they don't really like that because they're like, oh, fucking ethanol fuel. But I know in other countries they can just put ethanol in there as routine, so I'm not expecting to see a whole lot of ethanol come over. It's pretty common knowledge that there used to be lead in fuels. That's why we have unleaded fuel these days. A lot of people watching this would be around when you still had leaded fuel. It wasn't actually that long ago. If you actually think about what the actual lead chemical was, it's actually tetraethyl lead, which is an organometallic reagent. It's quite rare for an organometallic reagent to come into sort of household use in a way. Nowadays, because we had to take the lead out, but there's still that problem, whereas fuel, if it's like too flammable in a way, it can detonate in the engine rather than like burn in a controlled way, and that's called knocking because it makes the engine really loud noise in the engine because it's actually blowing up. There's a whole lot of things you can use in there in the fuel to prevent knocking, but there's actually been replacement organometallic reagents, and they're quite interesting because they're sort of the archetype of their structural class. If that makes any sense. So we've got the sandwich compound, which is ferrocene, which is a very interesting compound in itself. But we also have a piano stool complex, which is, that's the name of the structure for it, which is the manganese tricarbonyl. That's not his full name. Oh, what's the ring on top? Methylcyclopropene. It's hard to tell from researching this stuff, but I think there's probably that manganese compound in the Australian fuel. It's probably banned elsewhere, but I think it's in here. But it's at such a low rate. I think it's, 1 milligram per 100 litres of fuel. So, I'm not going to do an extraction of manganese from fuel. As interesting as that would be, because I'm not boiling down 200 litres of fuel, it would probably cause a fireball the size of my suburb. So, anyway. Alright, now the column is struggling, even though we're at, the boiling point down here, which is, if this thing decides to turn on, 110, so, we're looking at toluene kind of thing. It's hard to maintain the heat all through this column, so up here it's, mid-90s, and up here it's 50s. It's just the heat isn't really being maintained in here, and even though I've insulated the columns, the heat isn't being maintained. And because I've insulated, you know, these columns are, this bottom column's not doing anything, you know, it's just completely flooded. You know, I don't know much about fractional distillation, but I know enough to know when I'm doing badly. And this isn't really working. So I'm really going to have to reconfigure this setup to just have one column, which is a lot more sensible. The light is failing on me once again, but we've got a new setup, and you can see the condensation line moving up that column very nicely. And there's not a whole lot left, so we could possibly get there before the sun goes down, but perhaps not. Okay, and here are all our final distillate fractions. Some of the ranges overlap, but that's because I was just kind of recording it as I was seeing it. I was kind of not trying to imprint what I thought it should be, but actually like writing it down as it happened. So this was like the 72 to 90, you know, that came over really fast, and then I sort of took out another fraction, and nothing distilled over before 88, and then sort of 88 to 92. So, you know, there's a bit of overlap there, but I mean, really, the whole spectrum is completely continuous because there's so many compounds and so many azeotropes and quaternary azeotropes. It's all, you know, ridiculously complicated. But so now we have all these fractions, we can actually start applying what we know about the fuel to say what the major component of sort of most of these are. Very early on, we have very small amounts of some lighter boiling stuff, and this is probably also a consequence of the fuel I was using was quite old, and these are the compounds that will evaporate off first. And there's quite a lot of butane that was dissolved in there, and the Graham condenser obviously didn't capture it because the water just wasn't cold enough and it would just evaporate off. So we don't have any of the butane represented here. Pentane boils at 36, so this sort of early stuff is probably predominantly pentane. Up to 45 to 51, then we're starting to get branched hexane, all that sort of thing, but we're still definitely just in alkanes here. 52 to 57, same deal, you know, probably branched hexane. Hexane boils at 68, so this is probably hexane and any sort of hexane azeotropes. We're still predominantly just dealing with alkanes up to this point because the lightest aromatic is benzene, and that boils at 80.2, so it has, you know, azeotropes below that, but I'd say sort of up to here there's no aromatics. Next up we have 72 to 90, which is a big fraction, but we'd have things like benzene, the first of our aromatics, and also cyclohexane, which would be sort of the first of our cycloalkanes. You can also get stuff like cyclopentane, cyclobutane, but they sort of have such a ring strain that they don't really tend to exist so much, especially compared to cyclohexane. 88 to 92, 2,3-dimethylpentane boils at 90, so we'd expect it to be mostly in this fraction here, sort of the upper boiling fraction of that one, one of the main branched alkanes. 95 to 110, we'd expect there to be quite a lot of heptane. Heptane boils at 98, and heptane is a large component of fuel, so we expect there to be quite a lot of heptane in there, as well as, you know, a lot of branched things. Once again, out of order, but 110 is where we start to see toluene come over. We'd expect it to leak sort of into this fraction too with all the azeotropes, but toluene is a big component of petrol. There'd be quite a lot of it in there. Also, we have octane boils at 125, so this fraction we'd say is probably mostly octane, probably not straight octane, because when you get sort of that large a molecule with 8 carbons in a row, you've just got more chances for it to be branched. So statistically, they're more likely to be branched than straight, because it just gets distilled out of crude oil. So it's not like there's any reason that they'd be straight rather than branched. So statistically, by the time we get to octane, it's probably, you know, much more branched than it is straight. 132 and 138. It's quite a large fraction, and I can't really pin that down to too much. Although I'd expect sort of the xylene's a big component. That's dimethylbenzene. That boils 140. So there's probably quite a lot of xylene in this 132, 138, as well as this 142, 148. We could have nonane, you know, like 9 carbons and branched stuff. You know, that's probably in here as well. I would think that we're starting to sort of, there's not too much of the, sort of the 9 to 12 carbons. We expect there to be quite a lot of aromatics here up here. 150 to 160. We can't really contribute that to stuff like trimethylbenzene because trimethylbenzene doesn't boil until 170. So this could have a little bit of trimethylbenzene in there, but we're not going to have too much like tri-substituted aromatic stuff. It's also interesting to note that there's a bit of a yellow color. It sort of starts to come over here if you can just see it, and then these two are quite noticeably yellow. I don't know whether that's the dye coming over. That seems a little unlikely, even though it's the kind of the color of the dye. We'd expect most of the dye to stay in the pot and decompose like it looks like it has. So it could actually just be the color of the sort of heavily substituted aromatics. Above 160 is things like the tri-substituted benzene, the tetra-substituted benzene, 1, 2, 3, 4 tetramethylbenzene. I was hoping to be able to show you the difference in burning between some of these fractions, especially in the smoke that comes off them, because I thought that, well, we can kind of say that below this 72 here, there's no aromatic. By the end here, we're getting real heavily substituted aromatic. The difference in burning between aromatics and alkanes is that aromatics don't have a lot of hydrogens for their carbons, so they tend to burn with a real sooty flame, whereas alkanes burn a lot cleaner. But as we can see, they generally all have quite a soot-filled flame. That's probably because of alkenes that are just spread across all the fractions, because you can have any sort of number of alkenes, and also because, I'm not making any great claims about perfectly separating these, like there'll be mixtures of everything throughout every fraction. Alright, so the big question remains though, is a Graham condenser useless? Well, it kind of worked, but it pretty much sucked at condensing the low boiling stuff. And then with the higher boiling point stuff, the air condenser that we had to use in order to make the Graham condenser actually work and get it in a vertical position did most of the condensing anyway. And you can't avoid that even if you have a specially designed steel head with an elongated arm in order to use the Graham condenser. That's going to do heaps of your condensing work on high boiling point stuff anyway. For an item that costs more than all the other condensers, well, except for the real fancy ones, but out of the standard like All-In, Liebig, and Graham condenser, the Graham condenser is much more expensive, completely unversatile, and even when you have to use it in the particular setup, you need at least 1 or 2 more specialty items just to use it in that setup, and then it still doesn't do that great a job. So, it gets a solid 1 out of 10 in my condenser rating scale, which I just invented. Yes, I hope you enjoyed this video, and if you're a big fan of the Graham condenser, or in fact you're named Graham and you find offense at this video, let me know in the comments. If not, yes, just check out my other content. I don't usually say that. I don't know why I did say that, but I don't know, check it out. Whatever.